During last lecture we discussed about the anomalous behavior of oxygen and anomalous behavior of fluorine. Now in this lecture we are going to discuss about the chemical properties of elements of group 16, 17 and 18. Now first important chemical property, oxidation state of group 16 elements. The valential electronic configuration of group 16 element, it is Ns2Np4, because in outermost shell these elements, that is oxygen, sulfur, selenium, tellurium and polonium, these elements contain 6 electrons in outermost shell, and this is the valential electronic configuration. The common oxidation state of this element is -2 and +2. Actually oxygen shows always -2 oxidation state with the exception of hydrogen peroxide, whereas other elements also shows positive oxidation state, that is +2, even +4, +6. Now oxygen has -2 stable oxidation state, already I told you. In oxygen difluoride, exceptionally it shows +2 oxidation state, and hydrogen peroxide, its oxidation state is -1. Other elements like sulfur, selenium, tellurium and polonium shows +2, +4 and +6 oxidation states. The stability of +6 oxidation state decreases down the group, whereas stability of +4, that is lower oxidation state, increases down the group due to inert pair effect. What it means, when we proceed from sulfur to selenium to tellurium to polonium, that is down the group, the stability of +6 oxidation state decreases. It means +6, in case of polonium, +6 oxidation state is least stable, whereas in case of sulfur, +6 oxidation state is most stable. Whereas stability of +4 oxidation state increases. Polonium shows +4 stable oxidation state and sulfur shows +4 oxidation state, which is the less stable, and this is due to inert pair effect. Actually the inner shell s electrons, pair of s electrons, they are inert towards the oxidation, and because of that inert pair effect, the +4 oxidation state, stability of +4 oxidation state increases down the group. Then oxidation state of group 17 elements. Their valential electronic configuration is Ns2Np5. These elements contain 7 electrons in outermost shell, that is fluorine, chlorine, bromine, iodine and astatine. These elements shows or have 7 electrons in outermost shell, and therefore their common oxidation state is -1, because it is very easy for these elements to gain 1 electron and complete octet, and therefore their common oxidation state is -1. Additionally, chlorine, bromine and iodine shows positive oxidation states like +1, +3, +5 and +7. Iodine, especially iodine, shows +7 oxidation state. It can form IF7, iodine heptafluoride. In iodine heptafluoride, oxidation state of iodine is +7. Chlorine and bromine shows +4 and +6 oxidation states in oxides and oxyacids. Fluorine shows -1 oxidation state only. Positive oxidation state is not possible for fluorine. Then oxidation states of group 18 elements. As you know, group 18 elements, that is helium, neon, argon, krypton, xenon and radon, their electronic configuration is stable, and the outermost configuration here it is ns2np6. There are 8 electrons in outermost shell, and therefore resulting configuration is highly stable. And therefore these elements, group 18 elements, have less tendency or negligible tendency to lose or gain electrons. But xenon, recently it has been discovered that xenon can form certain fluorides or oxides, and the compounds of xenon, in compounds of xenon, xenon shows higher oxidation states like +4, +6. These are the some compounds of xenon, that is xenon difluoride, xenon tetrafluoride, xenon hexafluoride, xenon trioxide and xenon oxygen fluoride, tetrafluoride. So in most of the xenon compound, their oxidation state is +4 and +6. The next point is chemical reactivity towards hydrogen. First of all, chemical reactivity of group 16 element towards hydrogen. Now group 16 elements, that is sulfur, selenium, oxygen, sulfur, selenium, tellurium, these reacts with hydrogen and they form corresponding hydrides. For example, water, this is the hydride of oxygen. Then hydrogen sulfide, H2S, this is the hydride of sulfur. Similarly, hydrogen selenide and hydrogen telluride. So these hydrides, these are covalent, angular, and element like oxygen, sulfur, selenium and tellurium undergoes sp3 hybridization. Now what are the trends in different physical properties? First important trend is boiling point and melting point. So boiling point and melting point generally increases with increase in molecular weight. Actually water is expected to have lower boiling point. It should be before hydrogen sulfide, but unexpectedly water has higher boiling point than these other hydrides of sulfur, selenium and tellurium, and this is the trend from H2S to H2Se to H2T. Boiling point and melting point increases like this, and water has unexpectedly higher boiling point. Actually this higher boiling point of water, it is due to strong hydrogen bonding exists in water, and therefore it exists in liquid state and its boiling point is higher. Actually other are gases, water exists in liquid state. Then bond angles. So bond angle decreases from water to hydrogen sulfide to hydrogen selenide to hydrogen telluride. So bond angle decreases, and here is the trend. So bond angle decreases. For water it is 104, and for hydrogen telluride it is 90, and it is decreases from water to hydrogen telluride. Then acidic nature. Acidic nature of hydrides increases from water to hydrogen telluride. So here we can compare the pK value. Acidity is expressed in terms of pK. pK, it is a negative logarithm of K, and you know K, it is a dissociation constant of acid, and negative logarithm to the base 10 of dissociation constant of acid, this is nothing but pK, and smaller the value of pK, greater is the acidity. So hydrogen telluride, it is more acidic or most acidic, whereas water is least acidic as compared to other hydrides of this group number 16 elements. Then thermal stability decreases from water to hydrogen telluride. Reducing characters increases in this order for water reducing characters are less, whereas for hydrogen telluride reducing characters are more. Volatility. So H2S, it is most volatile. Actually H2S, H2SE and H2T, these are the gases. H2S is the most volatile. Actually water is expected to be least volatile, or sorry, most volatile compound, because its molecular weight is less as compared to other hydrates, but unexpectedly it is less volatile than H2S and other hydrates. Reason for this is, again, in water there is a hydrogen bonding and it exists in liquid state, and other hydrates are gases. So high boiling point and low volatility of water, it is due to hydrogen bonding. So this is about the chemical reactivity of group 16 elements towards hydrogen. They form hydrides, and these are the various trends in the hydrides. Additionally, bond length increases from water to hydrogen telluride. Then bond dissociation energy decreases from water to hydrogen telluride. So water has higher bond dissociation energy, whereas hydrogen telluride has least bond dissociation energy. So bond formation energy, positive value, increases from water to hydrogen telluride. So for examination point of view, there is no need to remember this data or all these numbers, just to remember these trends, and no need to mug up this table directly. Then chemical reactivity of group 17 elements towards hydrogen. So group 17 elements, these are the halogens: fluorine, chlorine, bromine, iodine and astatine. Astatine is a radioactive. So halogens react with hydrogen and they form hydrogen halides. For example, hydrogen fluoride, hydrogen chloride, hydrogen bromide and hydrogen iodide. These are the hydrides of various halogens. So boiling point increases from HCl to Hi. Unexpectedly, hydrogen fluoride has higher boiling point as compared to other hydrogen halides. So increases from boiling point and melting point increases from HCl to Hi, and HF exceptionally has highest boiling point. Bond length increases from HF to HCl to HBr to Hi. So bond length increases, bond strength decreases, and therefore Hi is bond between hydrogen and iodine is weak and it is most acidic. So acidic nature increases from hydrogen fluoride to hydrogen chloride to hydrogen bromide to Hi. It is expressed in terms of pKa. So hydrogen iodide has least pKa value and therefore it is most acidic as compared to other hydrogen halides. Then reducing characters increases from hydrogen fluoride to hydrogen chloride to hydrogen bromide to hydrogen iodide. Hydrogen iodide is the most it has most reducing character, because bond between hydrogen and iodine is weak, easily it is broken and hydrogen is available for reduction reaction. So Hi is good reducing agent. Thermal stability decreases from hydrogen fluoride to hydrogen iodide. Bond between hydrogen and fluorine is thermally stable, whereas bond between hydrogen and iodine, Hi bond, is least stable. It means when HF is heated, it is slightly resistant to heat, but Hi, it is easily broken. Covalent characters again increases from HF to HCl to HBr to Hi. So Hi is most covalent. And one more trend, bond dissociation energy decreases from HF to Hi. So this is about the